BC Calculus, Lesson 4.4, Derivatives of Exponential and Logarithmic Functions. Good news, this is like the last of the derivatives, which is kind of nice. And we get into exponential and logarithmic functions, and of course there's always something new and extra to learn, but we'll start with e to the x and derive the derivative. So we need one tool, and that's this one right here. And it's kind of tricky to see, but if you graph it, and I'm not going to save time, but I would highly recommend it, you'll see that it hits right here. I think it looks something like that at 1, and of course it's undefined at 1, but the limit, I'll write it out, as h approaches 0 of e to the h minus 1 over h is 1. So now we're going to do the limit of e to the x. We're going to find the derivative of e to the x. So dx of e to the x equals a limit as h approaches 0. And this is something you really should pause this and make sure you remember the definition. E of x plus h minus e of x over h equals if we have e to the x plus h, it's the same as writing it as e to the x times e to the h minus e to the x, which we can factor out in e to the x, left with e to the h minus 1, and we'll put the h under that just for the fun of it. And as we just showed up above, we get, I guess we can get rid of it, the limit as h approaches 0 is just 1, and we're left with e to the x, which makes no sense. I mean, what just happened? Well, basically, we just said that the derivative of e to the x is e to the x. And it's like, okay, that's funny. Try again. But no, that's actually what happens. So this is one of the best derivatives to do because you just say, well, it's the same thing. And then you just look at the chain rule. 2x plus 1. Done. If you are upset by that, I could write it as 1 plus 2x. I like 2x plus 1. So really, that's it. I wish I had more to go. So how about the derivative of a to the x? We have to assume the base is positive, not equal to 1. And we're going to do something called, excuse me, I got to look it up here real quick just to make sure I don't screw it up. Logarithmic differentiation. And it's really the only thing you need to remember. And the class I work with now is freakishly smart. They don't actually bother memorizing formulas. They just, differentiation, they just use the tools I give them and kind of run with it. So y equals a to the x. Take the natural log of both sides. All right. I guess I could rewrite this using a to the x, but yeah, it's kind of boring. So take the derivative of both sides. I can't do that yet. I don't have that tool available. My bad. So I do have to rewrite this using e to the power. So I'm going to rewrite this one as e to the natural log of a to the x. So, as you recall, they just cancel. I'm left with a to the x. Well, why did I do that? Well, whenever we have variable up here, we're going to get a log involved, and it's always going to be natural log. Regular logs are not what you use in calculus. And the reason we do that is we can take the x and throw it out front so that we end up with y equals e to the x ln of a. Take the derivative, and we get e to the x ln of a times, I feel like I'm messing this up. No, I'm good. Times the chain rule. x to the first just 1, and ln of a is constant. All right, so we end up with rewriting this back the way it was, just a to the x times ln of a, and that's the derivative. Don't forget your chain rule, of course. Notice a is a constant, so that's another stupid one, just like e to the x. It's the same thing with an ln a slapped on. And once we have the natural log tool, I end up doing almost all of these with logarithmic differentiation. So what point on the graph does the tangent line have a slope of 21? So let's go find slope. So dy dx equals 2 to the t, because it doesn't change, times natural log of 2. The other one cancels out at 0, so we end up with 21, because it's slope. So now we got to do some math. 2 to the t equals 21 over natural log of 2. I've got to take the natural log of both sides. Y to get the t out front, t natural log of 2 equals natural log of, holy moly, 21 over natural log of 2 divided by natural log of 2. And there's t. Put that in a calculator, blast it out, we'll get about 27, we'll get about 4.921. And there's lots of different ways you can do that by rewriting things, but I mean, that's what you're going to get, that's fine. And you plug that in, you'll see that, and I actually will plug that in, to the 4.921 minus 3. 2 to the 4.921 minus 3 is about 27. So, did I write it wrong? No, I wrote it right. Hmm. 2 to the 4.921 minus 3. Oh, so that's just the point where it's at. So what point is that at? That goes back to the original equation. At what point is 4.921, comma, bring that back up, 27.295. Sorry, I thought I was doing the slope. If you want to find out that slope works, then do 2 to the t times ln of 2 to the 4.921, 2 to the 4.921 times natural log of 2. Always do that. Times natural log of 2. There's 21. And there's the point. So what's the derivative of natural log of x? Y equals natural log of x e to the y equals e to the natural log of x equals x. Implicit differentiation, dx of e to the y equals d dx of x. We end up with e to the y dy dx equals 1 dy dx. I feel like I'm messing this up. No, I'm good. Equals 1 over e to the y, which, if we go back to the beginning, e to the y equals x. So we get dy dx equals 1 over x. Can't possibly overemphasize how much this one gets used in the world of natural logs. Pardon me, in the world of calculus. So be prepared for it. A line with slope m passes through the origin. It's tangent to the graph of y equals ln of x. Whenever I see origin in a problem, I write 0, 0. What's the value of m? So this looks like it's not too bad a problem, but it's actually pretty tricky. So we don't know the point, so let's make up a variable, a constant. We'll say it goes through some point in addition to the origin of a, and then if I put in a, I get ln of a out. So I want the slope, and I can do it the old-fashioned way. Ln of a minus 0 over a minus 0 equals ln of a over a. And I can do it with the derivative. dy dx equals 1 over x. That's the slope. 1 over x equals natural log of a over a. You say, well, I got two unknowns. Well, don't forget it goes to the point a ln of a. So that's x. 1 over a equals natural log of a over a by natural log of a equals 1. A equals e. Want to say e to the first, we can do that. Therefore, what's the slope? Slope equals 1 over x, 1 over a, equals 1 over e, or you could say e to the negative first. I just blew through that problem in a very short amount of time, but yeah, that's tricky stuff. No question about it. So find the derivative of log base a of x. So y equals log base a of x. And I know quite a few different ways to do this. A to the y equals x. Differentiate on both sides. As we know, we get a to the y when we differentiate this side. I'll write that in for you if you prefer. Dy dx equals 1. And I think I'm messing this up. Yeah, I don't want to do it this way. Yeah, I'll think about it. Yeah, I'm going to have trouble defining AY. Well, let's see where it takes me. I have a feeling this is going to screw up. Equals 1 over AY, a to the y, which is 1 over x, because a to the y equals x. But we're missing a piece of this, and I'm not sure where I messed up, so I'm going to leave this one out. I'm going to rewrite this as y equals natural log of x over natural log of a, which hopefully you've seen before. And then I'll come down here and take a standard derivative. 1 over x, natural log of a. Got to remember the chain rule, but it doesn't pop up. So where did I screw up on this one? A to the y equals x. Derivative of a to the y, there it is. Oh, I can't believe I did that. That's very disappointing. So I'll unerase this. And like I said, I just use this natural logarithm for everything and erase that. So it's a to the y natural log of a, which I knew, 1 over a to the y natural log of a equals 1 over x natural log of a. My apologies, I don't have all these memorized yet. I really should. And give it a shot. Dy dx equals 1 over, and like I said, I don't have it memorized, x, which is whatever was there, a to the sine of x times natural log of a times cosine of x. Chain rule and all that. Make sure I got that right. I'm looking up my answers. And I've screwed up. Yep, my bad. I jumped the chain rule there. So 1 over a to the sine of x times, remember, a to the sine of x, ln of a. So we had to do this part. Now we have to do this part. That's right there. And now we have to do this part. Cosine of x equals a to the sine of x ln of a over cosine of x times a to the sine of x ln of a. And this happens more often than I can even tell you. Cosine of x. And last but not least, find y prime. Well, you already know how to do this. Root 2 x to the root 2 minus 1. And we're just throwing an extra one in there to see if you know what's going on. I think that's it. Yeah. I guess there's one more. So, find the derivative and the domain. For the domain, look at the original. X minus 3 has to be greater than 0, can't equal 0. X has to be greater than 3. And then after you take the derivative, 1 over x minus 3 times 1 f prime of x equals 1 over x minus 3. Okay, according to that, it can't equal 3. It wasn't, so this is my domain. That's my derivative. And I already showed you logarithmic differentiation. So you go natural log of y equals x natural log of x, 1 over y dy dx equals x times 1 over x plus 1 times ln of x dy dx equals 1 plus natural log of x times y, which is x to the x. And I'm not going to lie, I think that's pretty freaking slick. So I rewrote all of these so you have them handy. That's it. As always, happy mathing.